All right, so as many of you know, I left my academic position a couple years ago to run a healthcare technology company. And so one of the things that allows me to do now is to come talk at meetings like this and poke and prod and ask some questions that maybe a lot of people are thinking, but nobody wants to say out loud. So that's kind of one of the things I'm going to do today. I also, let's see, oh yeah, I'm supposed to point it over there. Believe it or not, I have an undergraduate degree in mathematics, but I've been a card-carrying biologist for 30 years now. So it's been a lot of fun, and it's resonated with me, a lot of these mathematical models that we've seen today on the biology of aging. And as Brian said, we sort of talked a little bit about some of this when we were doing our early yeast studies. One of the things I want to caution, though, is to be a little bit careful about extrapolating from those mathematical models into the mechanisms, the biological mechanisms of aging. And one of the reasons why I want to suggest we be cautious is I think we fundamentally have a very low understanding of what the biology of aging is. So certainly we should develop hypotheses, we should test those hypotheses, but we should not get married to our models, and we should be willing to change the models as we get new data. So I don't know if we understand aging biology better than the people in 500 BC understood the surface of the Earth, but I'm not convinced we understand aging biology a lot better than that. There's a couple things to say about this. One is that means we have a lot to learn. It doesn't mean that our model of the biology of aging, and I'm using the Hallmarks obviously as a model, and we can talk more about whether that's a good model or not, doesn't mean that that model is not useful. This map in 500 BC was really useful for trade and economic expansion and probably warfare as well, but we've got a lot to learn. And so there's a lot of reasons, I think, to believe that that's true, that there's a lot we don't understand. One of the things I think about quite a bit is how slow, in many ways, the progress has been at identifying new ways to modify the biology of aging, at least to a significant extent in mammals. There are probably on the order of 8 or 9 genetic perturbations that robustly affect the aging process in mammals and in particular lifespan, and maybe about that many pharmacological non-genetic ways to do that. But I think without a doubt, the gold standard for non-genetic ways to modify lifespan in mammals is caloric restriction. This is a graphic from a book that Rick Weindruck and Roy Walford wrote back in the 1990s from an experiment that was done in the 1980s on caloric restriction in mice. This, I think, is pretty interesting. If you look at the median and maximum lifespan of these animals, it's quite long. We're talking, almost 60 months for maximum lifespan. To the best of my knowledge, nobody's done better than this since then with a non-genetic perturbation for longevity. So what does that mean, and why is that? Why can't we do better than caloric restriction? So I sort of used a tool to extract the data from this Weindruck and Walford paper, and it's actually pretty striking to me when you compare some of the interventions that most of us in the field are really excited about to the data from that paper. So these are just the controls and the treated group from the 60% caloric restriction from that 50-year-old paper now. Okay, here is, again, the best of my knowledge, the best effect from rapamycin that's ever been reported. This was a study from my lab. We treated the mice with rapamycin for 3 months. You can see nowhere near the magnitude of effect of caloric restriction. This is a recent study from Linda Partridge, trametinib plus rapamycin. Looks pretty comparable to our rapamycin alone effect. This is the IL-11 study that a lot of people were excited about. Looks pretty comparable to rapamycin alone, nowhere near the effect of caloric restriction. This is the best that I'm aware of for a senolytic, not even as good as rapamycin or IL-11. Sorry, Brian, this is alpha-ketoglutarate. Intermittent fasting, something that almost everybody in the field talks about as if it's this very potent way to slow aging. It's right on top of the controls from the Weindruck and Walford study. Metformin, right on top of the controls from the Weindruck and Walford study. So what does that mean? I think these are questions we should talk about and address. Nicotinamide riboside, very, very famous right on top of the controls. What about reprogramming? That's got to be better than caloric restriction, right? This is, again, to the best of my knowledge, the best effect of epigenetic reprogramming on longevity, not even as good as rapamycin. And in fact, I don't know if any of you guys saw this. It's a pretty interesting panel discussion that Hal Barron was involved in. I think Kristen Fortney was also in this panel. You should check it out if you get a chance. He basically said at Altos they haven't been able to do better than rapamycin with multiple rounds of epigenetic reprogramming. So why is that? Why do we keep hitting these barriers? So why can't we do better than caloric restriction? One possibility, and this kind of came up today, maybe CR represents kind of the best we're going to do in mice. Maybe we aren't going to be able to push past that. I personally don't think that's the case, but that's a possibility. Maybe it's just that nobody's looking. I actually think this is part of the explanation. I think when the hallmarks of aging sort of got formalized, the field became very narrow in scope, and everybody started trying to fit what they were doing into that context, and very few people kept doing discovery science, like the stuff that Brian and I were doing 20 years ago, or the RNAi screens that were done in C. elegans. If you look at drug age, this is the largest publicly available database of non-genetic interventions for longevity. This includes interventions in every organism that's out there. There are about 1,000 drugs that are listed in drug age. Now that's not everything that's ever been tested, for sure, but this is probably the best data set for quantitative effects on longevity from different interventions. It's only about 1,000, so it's a tiny, tiny fraction of the intervention space. Even if you were to just think about, pairwise combinations of FDA-approved drugs, that would dwarf this. And then we start getting into all the other types of molecules that are out there, and three-way combinations, four-way combinations. We have really explored a tiny fraction of intervention space. This is also true on the genetic side. I don't think a lot of people appreciate this. A lot of people in this room maybe think that we've really explored the genetic space for longevity well with the large-scale RNAi screens and deletion screens. It's useful to understand those were looking at really a single dose of the genetic perturbation, right? We're looking at really one level of knockdown. Nobody's done a genome-wide overexpression screen. Alateen Kaya has done a small screen overexpressing essential genes in yeast and actually found that something like 50% of them increased lifespan, a huge number. So there's a lot out there to be found, both genetic and pharmacological interventions. Nobody's looking right now, to the best of my knowledge. I think this is a big, big limitation in the field at this point, that we've kind of left behind big discovery science, and I'll come back to that. So one of the ways that we've tried to address this is through something called the Million Molecule Challenge. This is a company, Aura Biomedical, that we spun out of my lab at the University of Washington. Brian and Yong are both co-founders of Aura Biomedical. And this idea is to try to bring the community together to test 1 million plus chemical interventions for longevity in C. elegans. I think there's a lot of reasons why, especially if it's an open access data set, this would be really, really valuable for the community. The technology that enables this is called the WormBot. I'm not going to take you through how the WormBot works or what it does, but basically it's a robotic system combined with artificial intelligence that mostly automates the lifespan studies in C. elegans. And it's very feasible with only 100 of these things, which are pretty cheap to build, to test 1 million interventions in 2 years. It probably cost a few $1 million, but to my mind, given what we spend tens of millions of dollars on in this field, this should be a no-brainer. I think that the impact of having a data set like that, especially if it's available to the community, is really hard to underestimate. All right, so just to give you a little bit of a feel, so I think it's even when you get up to a couple thousand, this is just based on a couple thousand drugs that Aura has screened, you can start to identify patterns that are interesting. So this is an example looking at known, these are all FDA approved drugs. Biochemical targets, each bar here is a different biochemical target, and you can see there are multiple drugs that hit the same biochemical target that come out as increasing lifespan, decreasing lifespan. This is very simplistic, I know, analysis, but even with just a few thousand drugs, you can start to get interesting patterns. As you won't be surprised to learn, mTOR, whoops, is somewhere up here, but there are other things up here at the increasing lifespan that we didn't expect, right? And that's only going to increase with the size of the data set. You can do the same thing at the pathway level. You'll find pathways that come out enriched for things that increase lifespan, pathways that come out enriched for things that decrease lifespan. Again, only a couple thousand drugs versus the much larger space you could explore. And then I think we've heard combinations come up a couple of times today. I think we have almost no ability to model how combinations of drugs are going to interact to impact longevity or other age-related features. Okay, and then I think another possibility for why we haven't been able to do better than caloric restriction in 50 years, I'm going to say that again, in 50 years, nobody has done better than caloric restriction, might just be we don't really understand aging very well. And so we don't know how to do it, and maybe there's something fundamental about the biology of aging that we're missing. So again, I think biological aging is kind of poorly defined right now. I think one of the great things about this meeting, and hopefully what will come out of it, is we can maybe get to better theoretical and mathematical models for what aging is. And I think our existing clocks right now are really more noise than signal, and I think there's a lot of confusion about what we mean when we talk about biological aging clocks. Everybody's got a different clock or a different flavor of a clock, but everybody's calling them biological age, and I think that leads to a lot of confusion in the field. I'm guessing, anybody want to raise their hands who think the hallmarks of aging are a perfect model? Okay, we have one down here. So 99% of us would agree that the hallmarks of aging are not a perfect model. They're not terrible. They're telling us something about aging, but they're not a perfect model for aging. Okay, oh, they're not a model, they're a laundry list. Okay, so we have one strong opinion that they're a terrible non-model. So this is kind of the best consensus, though, for what people in the field would call biological aging, right? And I think we can mostly all agree that it's not a great, certainly not a complete picture of what biological aging is. And yet, many, many people in the field will point to measurements of one fraction of the hallmarks of aging and call that biological aging. I'm sure there are people in this room whose titles of their papers have used epigenetic clocks, and they've called it biological aging in the title of their paper. This is part of the problem I see in the field right now. And I don't think it's very scientific, but worse, I think it leads to sloppy thinking when in our own heads we start to make an equivalency between epigenetic changes and biological age. So personally, I think as a field, we should start to develop some consensus for how we're going to tackle this. So one of the questions I've got about the biological age clocks, and I'm going to talk specifically about the epigenetic age clocks right now because I think that's what I have the most personal experience in looking into, and it's what most people mean when they say biological aging, for better or worse. Why do they vary so much more than we expect? What does that mean? And over much shorter time frames. Why do they go up and down in a period of weeks, or some people even say in a circadian manner? What is that telling us about the biology of aging? That's certainly not the way I've thought about the biology of aging. I'm not saying it's wrong. Maybe it's telling us there's something about aging that's very different than what we anticipated, but it is the case that they go up and down, I think, in shorter time frames than at least most of us who were in the field 20, 30 years ago thinking about aging would have predicted. It's got to mean something. Why don't the biological age metrics match up to the rate of aging metrics, right? There's like the Dunedin pace, which is supposed to measure the rate of aging, but that doesn't match up to the actual measurements of so-called biological age with the same epigenetic samples. Why don't the different clocks match each other? Certainly I understand that they were developed based on different algorithms. And then personally, I'm wondering, why do the direct-to-consumer clocks suck as bad as they do? And in case you don't believe me that they suck, I did the experiment. So this is an experiment I did with 4 different companies that are out there. I did duplicate replicates, samples taken on the same day, the same biological samples if it was blood or saliva. Okay, here's the results. Like the data, I think, speak for themselves. So I was 53.5 when I did this, and you can see the data's pretty scattered, right? Now, if you take the average, it did converge on my chronological age, so I guess that's something. If I was to choose which company I like the most, I'd have to say Elysium. In my early 40s, according to Elysium. I really didn't like Tally Health. Sorry, David. That's just the way it is. But I think looking at this, like anybody with a statistical understanding would say this is not useful, right? This is not useful. And sure, you could say, well, maybe one company's good and one company's bad. How do we know? How does anybody at this point know? So this is a mess, guys. This is a mess. I don't know what consumers can get from this, but it's not useful, I don't think. So I also have longitudinal data on True Diagnostics. I'm sure many of you are familiar with True Diagnostics. I actually like the people at True Diagnostics. I think they're trying to do a good job. So I'm not trying to blast them at all. This is just what the data look like. So one of the things I find interesting here, so you can see the y-axis is the difference between the true age, their biological age metric, and my chronological age at the time of the test. So first time in December 2022, I was 6 years older based on their true age than my chronological age, and then I was younger, and then I was a little older, and then I was a little older. The thing I thought was interesting is they also tell you your Dunedin pace, which is supposed to be the rate at which you're aging, right? Okay, so first of all, if we just look at these numbers, between December and September or October of the next year, I aged at negative 15.8x, so that was great. But then I aged at positive 140x. That was really, I don't know what I did that month, but it was really not good. And then at a more sedate 3.8x, the normal rate of aging. But if we now compare this to my Dunedin pace, which is my rate of aging, supposedly, I was either at normal, or below normal this whole time. Again, it just doesn't make sense. So I'm not saying, first of all, I'm not saying Dunedin pace doesn't work or epigenetic age clocks don't work. I think as research tools, they're useful. Even there are some problems, but in the consumer space, this is not looking good. Okay, so my personal experience, I don't know if anybody else has tried this, but that's what I got. Okay, so then the last thing I want to talk about and touch on is AI. Again, this has come up a couple times today already. Will AI solve aging? So Ray Kurzweil, and I think many people are very bullish on AI solving aging. According to Ray, in 2032, 7 years from now, AI is going to solve aging. Okay, I don't know if that's going to happen. Like, definitely there's a lot happening in AI at an exponentially increasing rate, it feels like. To me, this seems very optimistic given the state of the knowledge in the field and the fact that we haven't done better than caloric restriction in 50 years. Maybe. I would suggest that it's not going to happen unless we get more data. So I think it was the last speaker who at the end said we need more data, and I've heard that a couple times. I think AI is only going to be able to do a good job of disentangling aging if we put good data in. And guess what? If you put metformin and rapamycin and caloric restriction in, guess what you're going to get out? So I thought this was pretty interesting. I'm sure many of you have heard of this. There's an interesting podcast as well about it, the Vivo Therapeutics open source on drug perturbations in cancer cell lines. So they were able to do, this is single cell RNA-seq, 100 million cells, 60,000 drug cell interactions, 50 cancer cell lines by 1,200 drugs. Single cell RNA-seq, and then try to create large language models that can disentangle this data. We should be able to do something like this for the longevity field. This is not beyond us to create this kind of a data set, open source it, and then let people go after it. So I think we need to get beyond just descriptive studies. I think for this sort of data moonshot that I would like to see happen in the field, we need to do more. We should characterize what aging looks like, for sure, at the molecular level, at all the phenotypic levels we can think of. I think we want to look across multiple model organisms. I would like to see perturbations, not just, again, characterizing what normal aging looks like, and the effective interventions. I think if we're able to get a large enough data set, then we can really harness the power of these tools that are coming online to really help us make advances in the field and maybe break through this barrier that seems to be there. Okay, and then last thing I'll say, if you liked this talk, there's a lot more where that came from. We've got a podcast, check it out, and I'll stop and happy to take questions if anybody has any. Go for it.
Me?
Yeah, go for it.
Great talk. I share your skepticism about the epigenetic clocks. So one factor that explains this variability that you're seeing are changes in immune cell type composition. So you're going to see huge variability in the fractions of the 12 of 19 immune cell types, major immune cell types that you have in blood.
Yeah.
And factors like jet lag or what you've eaten on the previous day is going to cause these fluctuations.
So I shouldn't take a biological age test right now.
So these clocks are fully confounded by that.
Yeah.
So I'm not surprised by...
Yeah, no, I thank you for that. And I agree. And I think we could probably spend the next hour talking about the causes of noise in the system. I think recognizing the noise is important. But yeah, thanks.
Very nice talk, Matt. I was just wondering about the sort of the lifespan comparison between different cohorts and interventions and stuff like that. So for example, in Europe, we have very strong regulation when you need to sack a mouse, which will impact, obviously, the lifespan and whether or not we're really measuring health span then or lifespan, or I think I feel it's sometimes difficult to compare between groups.
I think that's a fair point. I would question whether or not differences in the animal protocols really affect lifespan that much. I don't know the answer. That would be one question I would ask. My intuition is it might affect it a little bit, but it shouldn't affect it so much that the controls are so short that the long-lived treatment is where other controls are. That's my supposition. Your point is a good one. I think conditions definitely matter. And I think the comment that is often made is, well, we should just look at the difference between the controls and the treatment. I always wonder, why are the controls short-lived? And I will say it is my perception that many of the interventions that have failed to reproduce, when you go back to the original study, had short-lived controls, and the intervention brought it up to where the controls would have been in other studies. So your point is a good one. I'm just not sure how to handle it.
Thank you very much for this talk. Really fresh air for me in the realm of epigenetic clocks, because I agree with most statements you did. And in fact, the answers to the questions you asked regarding the clocks actually exist. I want to invite you to my tomorrow talk about these problems. But yes, thank you. But specifically, I really wanted to ask you another question. What is your definition, I mean molecular definition of aging? What's your...
That's a trap question, as I learned this morning.
But I don't need a precise question, but I want just your intuition.
Yeah, I mean, I think the honest answer is I don't have a good answer. It's something I think about a lot. I definitely gravitate towards, when I'm thinking about molecular causes of aging, the molecular changes, I'm not using the word damage, although that's what I think in my head, the damage that accumulates over time and leads to the functional declines that reduce health span and cause mortality, right? So, and that, you can think about functional declines at the cellular, tissue, organ, or whole animal level. But I think my intuition is there are a discrete set of types of damage that accumulate. That's why I don't think the hallmarks are terrible. I just think they're incomplete and we don't really understand the interactions between the hallmarks. But I've been around long enough to recognize that that is almost certainly a massively incomplete sort of conceptualization of what aging is. So I don't know the answer. I wish I did.
Really quick, one more.
Yeah, it's more of a comment, but also a question. So it seems like I'm really surprised that all the talks today has been treating aging as if that all cells and tissues age at the same rate.
Yeah.
And so when we think about, lifespan when a person dies, as if all the function shut down together. But that's not the case, right? We know that there are certain diseases are, older people are more prone to and lead to death because they cause, loss of essential function. So how come our aging study are not actually target specific cells and tissues that are weak links and age fast?
Good question. So I'll tell you how I think about it, which is, obviously we all think about this through our own experiences and framework. So starting in yeast many years ago, that's a single-celled organism. And so one of the things that has struck me is the fact that there are conserved mechanisms of aging and conserved genetic factors from a single-celled organism all the way to people. And there are single genes that can appear to significantly delay the aging process, meaning they slow functional declines and diseases and increase lifespan in every animal where we've tested this. This makes me believe that there is an underlying aging process that eventually manifests itself phenotypically as distinct diseases of aging or distinct tissue and organ function. And in individuals, the tissue and organs that are breaking down earliest are going to be different. There's a stochasticity there. So I think of, and again, this could be wrong, I think of age-related diseases as a phenotypic manifestation of the underlying aging process. And many times by the point it reaches clinical diagnosis of disease, the pathological process there is different than the biology of aging. One important implication of that is geroprotective interventions that slow aging or treat the biology of aging may not work once the disease pathology is no longer mechanistically shared with the biology of aging. So that's the way I think about it. I don't know if that's right or not, but that's how I conceptualize it.
So we're out of time, but I'll make a short exception if it's really a quick question.
It's a very quick question. I was actually surprised by the consumer clocks because I thought they would be worse. Because none of them showed.
You thought they'd be worse.
None of them showed your age like 40 or like below 40. None of them showed over 65. I think considering that they are less expensive and unclear, not unpublished clocks, it's actually pretty good, I think. So and that kind of leads to the comment of why you see this huge proliferation of aging clocks. It's like a glass half full or half empty, because we had nothing to measure aging, and now we are able to measure to some degree, whether it's a transcriptomic or epigenetic clocks, and with all this imperfectness, I think it's a major advance. That's why people use it, and there's exponential increase in the use of these biomarkers.
Yeah, so two comments. One, I agree with you from the perspective that we have lots of different tools that we can use that measure different aspects of aging. No question about it. That's been an advance. It's problematic when we don't know whether they're actually accurate or not, but that's a different question. I think the idea that confusing and misleading consumers is a good thing, I would push back. And you didn't say that, but I think we want to be careful that as scientists, we are not saying that it's okay to deceive, confuse, mislead consumers into thinking that we are measuring something that we have no evidence we can actually measure in those tests. So that's my personal view on this. And I think you could say, yeah, it's a good thing, it brings attention to the field. You could also say, well, maybe it's a bad thing, because when people stop trusting us, it's game over. So that's the way I think about it.
It's not what I'm saying, of course. I'm as skeptical as you about consumer clocks. I advise everybody not to use it. I've never advised anybody to use it. But I think we have to be realistic and realize that this is a major advance in terms of measurement. If we have two groups of people, like 20-year-old and 60-year-old, without knowing, just have a blood samples, how would you measure their age?
You look at them. So I agree with you. Again, I'm being a little bit facetious, but I would say we've had ways to assess age for a long time. You're right. You're right. It is an advance. I absolutely agree. Having many tools that can estimate. I even hesitate to use the word biological age because it means something different when somebody says, well, this epigenetic clock is biological age, this transcriptomic clock is biological age, but some aspect of biological age which is correlated with health outcomes and mortality. That is a good thing that we have those tools. That is an advance in the science. It also clouds the picture when scientists all use different definitions of biological age in the literature and in their papers, and nobody really knows what that means anymore. It's kind of like health span. Like, what do we even mean when we put health span in the title of our
Same papers? As aging. Nobody knows.
Yeah, fair enough. All right, thank you.
Thanks, Matt.